computer. So again, we're in the section C programming in Unix. This is a new section. Wait. Yeah. So let's say we have, like I said, let's say we have a program written in C. We're going to save it with a .c at the end. And now we want to compile it. So this arrow means that I'm at the command prompt. I'm like at the black window. And I can type GCC and then the file name. And this will produce a file named a.out, which is the executable version of the program of the file.c. In other words, my program, hello world, I'll do GCC file.c, and then I'll get a new file created in my directory called a.out, which itself is a compiled version of that program. So now I can run a.out and it'll print hello world. How do I run it? I just type the name a.out, enter.
Why is it called a.out? Where did the A come from?
That's just the default name.
And what would there be if you made two files? Would the next one be called B?
No, it would be overwritten.
Oh, okay.
You'd lose the first one. So actually, because of that, you don't want it just to have that default name. So the next line here, what I do is I'm compiling it with a flag -o file, and then the file c.c. That's the same file.c that I had in the first case. But this file here is the new name I want to give the output. Now I won't have a file called a.out. I have a file called file.
.out?
No .out, just called file. Whatever, if I want it to be called file.out, I'll write here file.out.
Okay. I just don't know the rules. Like, does it have to be called .out? Does it not?
No, it doesn't have to be called .out. That's just a default name. In other words, the default name is a.out, but I can call whatever I want. I call file. That's very useful. If I write a program which is a web browser, so I'll write, and it's a great web browser, and I want to give it to all my friends, I'll write GCC -o Nachum browser, and then I'll write file.c, and file.c is the actual program. And now I'll give everybody the compiled version, and they'll just see a program called Nachum browser. Whatever name I want to give it, that's the name of the program. So that's really great. Okay, so we saw the -o flag for GCC. There's another flag for GCC, which is called -wall with a capital W and a colon here. This will check not only for errors, because when you normally compile the program, if you do GCC file.c, if it doesn't compile, it'll print all the errors. And you'll see all the errors on the screen, and you won't get an a.out file, and you'll get a lot of errors. But that's just the normal errors. If you type W -wall, it'll check not only for errors, but also for all kinds of warnings, like unused variable errors. In other words, if you declared a variable int a and then never used it, that's kosher. It's not going to give an error, but it looks like a mistake because, like, maybe you meant to use it and you forgot to. So wall will give you more checks, which is very useful if you're a programmer. So that's another flag. Now we're going into a little bit of a complicated thing here. I don't know if did anybody learn about header files? Creating header files?
In the beginning.
Yeah.
Maybe. So let's say we have there's such a thing as a header file. And let's see what it is. Here's a program, hello.c. That's the name of the program. And here's the content. It's a very simple program. Notice all it does is run a function called print hello. But where is print hello? I don't see any definition of that in this file. If I would just run this file, if I would try to compile this file, it would fail and say, where's the definition of this function, print hello? But then I look at the top and I see, oh, include hello header.h. So that's going to tell me that if I can't just use this function, when I compile this function, also compile with it, or this function, this program only will work if you also include a header file. What header file? this hello header.h. So here it is. And now this file only has one line in it. It's just it's not the actual function. It's just the description of the function. But it does tell me at least what parameter it needs to get and what parameter it returns. So therefore, the compiler can know if this is a proper call or not, if that's a syntax error. So he needs that. But it's still not going to work unless I also include the actual function. So look, here's the actual function. My print hello, here is the name of the function, and it does printf hello make files, whatever, hello world. I just called it hello make files, return. So, and that one itself includes standard io.h, and this includes hello header also, this hello header. So now I got three files. One is a header file. One is the file that actually defines it. Notice it's called hello function.c. And that's it. Those are my three files. Now, how do I compile those three files? I need to, if I just try to compile this without telling it where these other files are, it's not going to work. So I do like this. GCC -o hello. That's the name of the file I want to give. I want to create. Hello.c is this first file, and hello func.c is the second file. I don't need to give it the header file. I included the header file, but I don't need to give it the header file. I'll just give it the two actual files. Now, I do the -i, capital I. So this will compile two files that both are C files, the n.c, and makes an executable file called hello. The capital I is included so that GCC will look in the current directory, which is dot, for the include file dot header hello header.h. Now, since I included this, he needs to know where to look for it. It could be in some other directory. I didn't need to do that for stdio. Stdio is standard input output. He knows where to look for that. But this one, since I made it, he doesn't know where to look for that. Theoretically, if I would put this header file in the location where stdio is located, then it would also work. I wouldn't have to write the minus capital I. I wouldn't have to write. But since it's in my local directory, I have to write -i. I don't remember what the I stands for. Maybe include. I don't know. Maybe.
Question real quick.
Yeah.
Instead of writing out every single file name that you need to compile, could you just write *.c?
Yeah, you could write *.c, but then there might be some other C file in your directory that you don't want to include. You see? So you could do that if you knew for sure, if you were working in a separate directory and all the files there were related to hello, then you could just do *.c. Yeah. The shell would fill it in for you, you see. The GCC doesn't know anything about it. The GCC, for his perspective, he's getting the same thing. He doesn't know. But the shell will see the asterisk and fill it out for you. That's how the two, you understand what I'm saying? It's not the job of JCC to figure that out. It's the job of the shell to figure that out. So yes, that would work, but we're going to see another way called make files. And this is a very useful thing. It's just to save you some typing. People make a big deal out of it, and it can be a big deal. It can be used in complicated ways. But for us, we're just going to think of it as a way to save some typing. Now, first, I'll just explain just a simple usage of a make file, which is kind of pointless, but it's just to understand something. Create an empty directory called my project, containing a file called make file with this content. Maybe we should do it, actually. So let me stop this share and go like that. Just a second. And I'll bring up this Okay. Screen share. Yofi. You can see the screen that I typed in?
Yeah.
Yes, we can see.
Excellent. Oh, what happened here? Okay, so let's say I go like this. Let's say MK dear, my project. A CD, my project. Okay, let's do like this. Cat, or not cat. I still haven't put in a good editor here. Echo, say hello, colon, into make file.
You mismatched your quotes.
Oh yeah. Oh no, that's that's not what I wanted. Sorry. Okay. RM. Oh, again, I did it wrong. Here, I need a quote. Okay. All right, well, whatever. That space was a mistake. Ugh. Silly how I'm doing here. Sorry about this. Okay, echo hello world. Fine. And now, if I type make, let's see if that works. I have to sudo, I have to install it. I don't know if it's going to work.
Are you trying to do?
Well, it doesn't have the function, it doesn't have the program make. So I have to install it. That's the problem with demonstrating things on your computer. If you didn't try it ahead of time, make sure everything works. Oh, but I don't remember my password. That's the problem. I had this problem before. All right. Never mind, I'll do like this. Okay. Okay, so if I do cat make file, I see I have a file that says like that. Now, if I type make, it does two things. It tells me what it's about to run, and then it runs it. See what I did?
Yeah.
It told me what I was about to run out of a courtesy, and then it ran it. Essentially, it could have just written, now there might be a flag you can give it make to be silent or something, where it won't tell you that, but essentially it just printed hello world. Now, why did it print hello world? I didn't actually say, what if I type like this? Make, say, hello. You see, that also worked. Now, if I go back to the file, I can do another one like say bye. Echo goodbye. Good, yeah. Okay. Let's just look at the file again. Now I have essentially two things. Now, what if I do make, it just does the first one. But if I do make and I tell it which one I want, what is it? Say underscore by. It'll do the by. So let's review what we just figured out. What we see is that you can make something called a make file. And then when you type the command make, which is a special command, it looks for a file called make file. And it runs the first command in the file. Unless I specify which command I want it to run, in which case it'll run the command that I specified. Is that clear? So,
Yeah.
so what if I did something like this? Well, I mean, I don't have these things here, but this is not going to work, but I'll just show you for the sake of argument. If I would write, for example, let's say I have a program called, my, and you're too close, you might scratch you. My prog. Yeah. And then I could write like, for example, or I could write, yeah, I could write like this. Ooh, what did I do there? What did I do? Why is it doing that in pink? Why is that? Why did that become pink? I don't know. I can do G. Oh, because it isn't capital. GCC minus O my prog my prog dot C, my other prog dot C, whatever, minus capital I. So now, what is it going to do if I type make my prog? What do you guys say?
Well, there's no actual C file, so it'll probably fail.
It'll fail, but what'll it try to do?
We'll try to compile some C
Exactly.
code.
Oh, I made a mistake. I think I made a syntax error. What? Oh, did I make a syntax error? Let's try that again. I don't know. I made some kind of error, but that's the basic idea. It'll try to compile those programs. So then I don't have to type. So like I said, this is just to save typing. Here, let's go back to my slides. Aiden, you're gonna get scratched. You're doing exactly what causes you to be scratched. You're teasing her. You don't think you're teasing her. You're teasing her. And you're bothering me because I'm teaching right now. So you have to go. Okay. You heard me? Okay, so we're back here. And we saw the hello world. In the above example, say hello behaves like a function name. And if I write make, say hello, it's like a function. It's like I'm running it. It's called a target, though. If you think about it, it's like a target. It's like a label with a colon. Okay. Using a make file to save typing. So I can write like this. Hello make. She's gonna scratch you, Aiden. Get out of here. Hello make. This is what I forgot to do this. I need to write, even though logically I shouldn't have to do this. I need to write the names. For logically, I should just write hello make colon and then the thing I want to do, like I did. The output file, the two files, the minus I. But I forgot. I have to also write this thing here. Put this rule into a file called makefile or makefile, and then type make, and the command on the command line, and it will execute the compile command as you've written it in the makefile. Note that make with no arguments executes the first rule in the file. We saw that. Furthermore, by putting the list of files on which the command depends on the first line after the colon, that's what I did over here, make knows that the rule hello make needs to be executed if any of those files change. That's a different one. So I don't know why it didn't work, but that's adding a separate thing, which is that let's say I write make on, I do make hello, but really none of the files changed. Then it won't run. It'll only run it if one of them has changed. You see what I mean? In other words, make it smart enough to know if these have changed since the last make. One very important thing to note is that there is a tab before the GCC command. Oh, that's what I'm missing. I didn't have a proper tab. I tried to make, right. in the make file. There must be a tab at the beginning of any command. So remember, I always had it indented here. It has to be a tab. So I think I forgot the tab. Okay. So if we go back, well, I don't want to go back, but I forgot a tab. That was the real problem. This is just an extra thing that prevents you from compiling when you don't need to. Now we get a little more complicated. I can also make variables for clarity. So I can say that I can make CC is a variable which has the value GCC. And I can write C flags as the value -I. And now I can write, when he types hello make, I can run the variable CC. And that's useful because I may have many places in my make file. I may make a make file for compiling many programs. And I want to define the compiler at only once at the top. And then if I decide to use a different compiler, I'll just change it at the top here. And then all the places that I used it will change. So I can make a variable. But they're not regular variable names. They're special variable names. This CC is actually a macro. And it's defined to be the compiler to use when you're using, C stands for C compiler. And the C flags is the list of flags to pass to the compilation command when I'm running the C compiler. So since I'm running the C compiler here, I can define my flags and then I don't need to write them here. Because it's a C flags and I'm writing CC. So because it sees that it's CC, it knows to automatically put the flags at the end here. So this will save me typing the flags for every single program that I'm running. So you see, it's just to save you typing. By putting the object files, like in this case, what am I doing here? By the way, these are object files. These are not the C files. Right. If I put the object files, it automatically will know to compile the C version and then create this file and then compile this. Anyway, this is getting a little bit complicated. The main point is you can use these flags and to use these labels or targets, and you can save yourself typing. And you look a little bit more professional if you're using a make file than if you're on the command line every time typing it out. Okay, so that's just how to compile. Okay, any questions on that?
No.
You sure? Okay, so now we're going to go to some functions. Basically, we're just going to learn a whole lot of functions in C. These are like built-in functions that all of them you can go to the manual and type in man open. Well, you have to go either 2 or 3, one of those sections of the manual page. Anyway, you do man open and you'll see there's a function called open. Man means like, tell me the manual page, give me the manual for, or the description of the function open. And open is a very basic operating system service, which allows you to open a file. So most basically, I got to give it the name of the path. In other words, where the file is, what file I want to open. And it gives me back an integer. And that integer is called a file descriptor. So you could say that it converts a path name into a file descriptor. You give it a path name, which is a string, like where the file that I want to open is, it's always relative to the location where my C program is. In other words, if I put this open in a C program in a directory called my project or my program, and it's right there, and the file I want to open is in that same directory, then I'll just write // or even without a // just write the name of the file. It'll automatically look where I am. If I want to go up one directory, I'll write // In other words, whatever the relative path name. I can also give it an absolute path name, specifying from /. So the open system call is used to convert a path name into a file descriptor. And a file descriptor is a small non-negative integer used in subsequent input-output. For example, read and write, if I want to write to the file. So basically the idea of using a file is first you open it, and then you read it or write it. What number will be returned? What number will be in this integer? So it'll be the smallest number possible. It'll have to be in positive number, a whole number, but the smallest one that is available. Now, that means that if a bunch of file descriptors have already been used, I'm going to get the next number in line. If I opened up 10 files, my file descriptor might be something like 13 or 14, 12. But it'll be the lowest number integer will be assigned to that file. So it basically creates a new open file. And the point the file offset is set to the beginning of the file. Now, what are flags? Flags are how to open the file. I can either open it for, O stands for open, R stands for read, RD, sorry, stands for read only, open write only, or open read and write. So that'll allow you to open the file only for read or only for write or both. The flag could also be append, which means instead of starting at the beginning for write, if you open it at the beginning for write, if you open it normal write only, you'll start at the beginning and you'll start writing over what's ever in the file. But if you do append, you'll start at the end of the file. And create will create the file if it doesn't already exist. Whereas open read only will fail if the file doesn't exist. Create will if the file exists and you do create, it'll succeed though. In other words, it'll overwrite. And the flags could be ORed together. So for example, I could do read only and append, write only and append. In fact, I don't think I can use the append and the create separately. I have to create it, but how do I want to create it? For reading or for writing? Or for, I mean, it doesn't make sense for reading, but for writing or read and writing, how do I want to open it? And then the final thing is this mode here, which is, you see, optional. And it's in brackets, that means it's optional. And the mode is, fine, I opened the file, but when I finish and I close the file, what permissions will it have? So that's the permissions here. 644, read, write, and read.
What's the 0?
The 0, because there's another, I think you don't really, I'm not sure if you really need it because a leading 0 should be ignored. But I think I think you can write there, there's another bit which you didn't discuss with the sticky bit, whether it's lit or not. I think it's for another purpose. I'm not going to talk about right now.
Wait, that argument is it's a mode type or it's just an int?
No, this is a mode. Remember we learned about modes, how you could define them by like 777 is the everything.
Yeah.
So this is the mode 644. I opened it so that when I eventually close the file, it'll be in mode 644.
Uh-huh.
I'm creating a file or I'm opening a file, but what do I want that file? What permissions do I want it to have? No? Okay.
Yeah, I heard. Thanks.
So here are the modes. But we know this already, right? but you can have these symbolic constants for these modes. In other words, you can have all these modes, and you can, instead of writing the number, you can write these letters. Read, write, execute for other. Right?
I feel like the numbers are so much clearer than the random gibberish letters.
Well, they're not really random gibberish. They're
No, I know, but like the numbers tell you exactly what permissions go where.
yes, the numbers are better. I almost never use the letters. I only use the numbers, but I try to teach the letters just so you know both. A word about file descriptors. The operating system maintains a file descriptor table for each process. So that's a very important point, which I emphasize when I teach operating systems, which is that a lot of people think, oh, there's a file descriptor table, there's a file table of all the files that are open that the operating system says it keeps. Well, that's true. That sentence is true. The operating system keeps a table of all the files that are open. But what's misleading about that statement is that it's the full truth. It's the truth, but it's not the whole truth, because the sentence should really continue for each process. And it's not one huge file descriptor, one huge file table. It's one for each process. So when the process is created, there will be 3 file descriptors automatically filled out for it. And what are they? 0, 1, and 2, the first 3. And 0, I think we learned this. 0 is the standard input, which is the keyboard. 1 is the standard output, which is the screen. And my cat is touching the screen. And 2 is the standard error. We talked about this, right? Do you remember we talked about this?
Yeah.
Yeah, okay. So when an open is subsequently called to open a file, open will return the lowest free file descriptor. So in this case, on a new system, on a new shell that I opened up, it's going to return the number 3. I kind of know for sure that it's going to be the number 3, because I know this cat is getting in the way. 0, 1, and 2 are already taken. So 3 will be the first file that I open up. A row will then be added to the table indicating what file 3 refers to. So something like 3 and then the path of the file. That's what the operating system is containing. Question?
Can you redirect, like for any arbitrary process, can I redirect one of the, what's it called? One of like the file descriptors? Not file descriptor, the stream, like.
Yeah, we'll learn how to do that. We'll learn how to do it in C. We did it already in the command line. Now we're going to learn how to do it. We learned how to ask the shell to do it for us. Now we're going to learn how to program the shell, how to write our own shell.
Can you do it on the fly while the process is running, or only like before launching the process?
No, you can do it while it's running. We'll see. Reads data from the file. So we did open. The next thing we're going to do is read the file. So we have a similar type thing, but now what we do is we take the FD that we got from the open. The open gave us a file descriptor. Now we got that file descriptor. We're going to read from the file. So we don't specify the path anymore. We use the file descriptor that we got. And we have 2 more variables, which are quite obvious. The size of our buffer, not the size of the file. We don't know how big the file is. By logic, by definition almost, we wouldn't know the size of the file. Could be anything. But we did make a buffer to read in our program somewhere. We had to make a buffer so that as we read the file by whatever size we want, size by size, we need to, let's say it's 500 bytes. So we read 500 bytes and it goes into buffer. 500 bytes goes buffer. But in order for the read to work, we need to know how big the buffer is. So we write here 500, if that's the size of our buffer. So this is the size of the buffer. This is a pointer to the buffer. Of course, the buffer will be defined above in some kind of, array that I made. We'll see an example. And this is the file descriptor I got. Now, what is this s size underscore t? That is something that's similar to an int. It's really, imagine it just says int there. And that int is how much represents how much was read. Because I made the buffer 500, but it could be the file has only 400 letters in it. So this size S, this S size T will be 400, will be only the actual amount that I read. If it returns 0, then that means I read 0. Here's an interesting thing. If count is 0, in other words, I give it a buffer where I tell it the buffer is of size 0, then by definition, read will return 0. I don't know why I wrote that, but yeah, it's true. If the number, now what about this? What if the number of size read equals the count size? What does that indicate?
If the amount
Wait,
read-
if what?
We reach the end of the file, right?
not necessarily.
Or
No,
that we
the
should load
opposite.
more in from storage?
The opposite. If this count size equals the S size, it indicates the opposite that we reach the end of the file. What does it indicate?
Well, you could have
Means
reached
we
it.
read everything that we were supposed to.
We read as much as we could, and probably there's more to read in the file, right? It could be that we exactly got to the end and there's nothing left. But it does indicate to us that we need to do another read, because just to know. But if our count size, if our read size is less than the count size, then what do we know?
Then we reached the end of the file.
Then we for sure reach the end of the file. In other words, if the count is equal to, then we probably didn't read the end of the file. We could have, but probably didn't. But then we'll have to, either way, we'll have to assume we did not finish the end of the file. We'll have to do another read. But once we get a size amount read is being less than the full size of the buffer, then we know we're done. Okay, and if it returns -1, of course, you can't read -1 bytes from a file. So -1 is used to indicate that some kind of error occurred. Okay, so here is a file, a program. I have a lot of includes, probably don't need all of them, but I hope some of them I for sure need. And I say, like, by the way, if you want to know what to include, whenever you go to the manual page, it tells you what you need to include at the top. You must include UNIX standard library. This one, I didn't write it, but sometimes I write. But every manual page will tell you what functions you need to include in order for, the function itself to work. So I put in a whole lot of things here, probably because I was working with some longer program and I cut it up. Anyway, here's a bunch of integers. Number read in. Number read in. Buffer here, I made a buffer of 256. The size is arbitrary. Now open a file for read only. And here I do open a file called file.txt. Open it for read only. And the file descriptor is FD. Now I check. By the way, you should always check if you got an error. If FD is less than 0, well, that means it's -1 or something. So it's an error. If we fail to open the file, print file not opened, exit. As the program didn't work. Good to have that exit there. You don't want to keep going if you got an error. Now we will read the contents of the file. So number read in equals read from the file descriptor that I got. I know this file descriptor worked because I checked if it didn't work, if it didn't succeed. In other words, why would it not succeed? Could be this file, I mistyped it, there's a typo there. It could be, it doesn't exist at all. It could be the file itself has no permissions, is zero, I don't have the rights to open it for reading. So that's why you always should check. Whenever you're doing something that's dealing with the outside world, you have to check for errors. In the real world, there's a file. Maybe I can't open it. So now I got my file descriptor from here, whatever number it was, probably 3. And then I write it to the buffer and I write 255. I don't want to fill the whole buffer. We're going to read one less. There's a reason for that, which I talked about, I think, once before. But I just read one less. Now, well, we'll see why exactly. We'll see because the next line here. Now, I close it. I finished. I read something, and I don't really care if there's more or not more. Could be there's more in the file, not, but I finished my loop. I didn't do a loop. I just read once. I closed. Now I want to print it. But in order to print it, I have to have a null at the end of the string. Now, I don't know if there is a null that I read or not, but I'm going to put a null in myself. Where will I put it? I'll put it exactly at number read in, because if I read 10 things, then that means that the array buffer has from 0 to 9 numbers, letters. And at place 10, which is the number read in, I read 10 things, I want to put a null. And that I do just so that the printf will work. It's the same with cout, you need to have a null at the end. So then I print, first I print the number read in as a decimal number. We saw this syntax of printf when we were learning awk. Was it awk? Yeah, I think it was awk. We saw this syntax. Awk has two kinds of print. It has regular print and printf. So %d means a decimal number. That's what D stands for. And then I put the number after the comma here. And then print another line with \n is a new line with a string. What string? The string that buffer points to. And this line will only work if I put that null there. Any questions on that? You can close a file descriptor with the function close. So you just write close, FD. Closes the file descriptor so that it no longer refers to any file and may be reused if I do another open. All open files will automatically be closed when your program finishes. Here's another program. I create my numbers, my buffers, and I open a file for read only, and I check if it failed. Now we will read the content of the file. So I read in something from the buffer. So far it's all the same, and I close. And I put the null. Why is this different from what we did before? Am I losing my mind? Oh, I just was on the wrong. Yeah, it is exactly the same we did before. How did I get there twice? Okay. I'm a little bit, no. Is this one? Okay. So we did close. I must have pressed the up arrow instead. Now we have write. Write is the opposite of read. It writes. So it takes the same parameters though. How much to write, or how big? Yeah, how much to write. The buffer, the total. This is really how much to write, not the whole size of the buffer. In other words, my buffer could have 100 things in it, but if I write 10 here, it'll only write 10 things. And the number of bytes written is also put in S size. And even if I wrote 10 here, it might be that I only wrote 3 things here. So that's why I need that, because I don't know what's really in the buffer. Maybe there's only 3 things in the buffer. Or actually, that doesn't make sense what I said. It's going to write everything that's in the buffer, whatever the size is. The reason that it wouldn't fully write is because I wrote here that the disk could be full. I could be writing to the disk and there's no more space to write. Okay, so here's an example of writing, and I have my buffer, and I open the file for write only, and this is going to potentially overwrite the contents of the file. I check for error, always check for error. And the read, I read the file and I print out, wait a second. I read, no, what do I read? I don't read the file. Notice I opened the file, FD is my file. What did I read from here? What's 0? Somebody, what's 0.2? What file descriptor is 0?
Root?
No,
Standard input keyboard.
right, look here. 0 is the standard input at the keyboard. So I read from the keyboard. This is like cin. This is one way to read from the keyboard. There's also scanf if you as the opposite of printf, scanf. But here's the most basic function, the most primitive. This is a service of the operating system. Read. It's called a system call. Read from the keyboard into the buffer up to 256 bytes. Now, notice I'm not reading 255 because I'm not printing it right now, but we'll see. Okay, I mean, probably I should have done that, but anyway, print number, what's number? How much I actually read. I'm just curious how much I actually read, so I printed. This is like kind of debugging. You can print, what you got just to see if you got something. And then write into FD, into that file from the buffer. Well, the buffer got filled up over here from the keyboard. The guy typed something and it went to the buffer. Now I'm writing the buffer. How much is the buffer? How much I got, the number of things that I got into whatever FD is pointing to, which is this file.txt. Then close FD. And now I have put it into my file. Well, wait a second. Before I close, I skipped a line here because I didn't notice, but there's this line here. What does this mean? Write to 1. What does write to 1 mean? So it says here,
Standard output.
write to the standard output, the screen. So in other words, instead of using printf now, I'm printing to the screen using write. So here you have an example of what we say about UNIX, that everything is a file. The screen is a file. I can write to it by its number. Just like I write to a file, I can write to the screen. And now I've written whatever the guy typed, I wrote it back to him. And then I close the file. And then I print it, and I print via printf, and I print it again, the buffer. Just showing you that I can print it either by printf or by write. So what I did was I read something from the keyboard. I stored it in a file. I then printed it to the screen twice. Now there's a set of wrapper functions to make it easier for people who don't like to use read and write. I personally like to use read and write, but there are some conveniences of using another set of functions called instead of open, there's an F open. Instead of read, there's F read. And there's F seek and rewind. And these are all functions for files. That's what it means, F open, file open. We call it F open. These functions actually call the lower level read, write, and open functions. We'll see an example on the next slide. There's a longer example, more funny things here. Yes. Okay, you gotta go. You gotta go. Okay. So we actually are going to use a different file type called a file. Instead, and notice a pointer. We're not actually using a file descriptor. We used before was a simple file descriptor, which is of type int. Now we're going to use a special type called file, the UNIX type, and a pointer to it. So it's called a file pointer, not a file descriptor. And we're going to make our buffer, and we're going to make a bigger buffer, 35 and 350. And we have some variables. And now we're going to use F open. And then I write the path of the file, stom.txt, and I just wrote R for read. Notice that that's like simpler than this open. I have to remember this long define here. Otherwise, basically the same. I mean, I don't see it as so different. So I opened it. That's F open. And now I check again that FP is not null. Before I was checking that it was a negative number. Now I'm checking that it's not null. Because, right, I'm gonna check that it's not null. Why? Because it's a pointer to a file. It's always gonna be, even if it's not gonna be 0, because there's no address 0 is not a valid address. So I'm just checking that it's not 0, essentially. 0 before was a valid address, but here it's not a valid address because it's if 0 before was a valid response because it wasn't an address, it was just a number, as long as it's positive. But here, 0 is invalid. So I'll check if it's 0, then it was a file didn't open, return 0. Now I'm going to do, wait. Oh, this is all comment, this f read. So forget about that. Here, f read, I don't know why I left it there. I should have deleted it. F read into the buffer, 35, and then size of character, the size of the thing that I'm reading, because remember, I could also be reading, it allows me to read like integers or, which are 4 bytes. So I need to do a size of the thing that I'm reading. And in this case, I'm reading characters. So I do a size of character. That function, size of, will return me the length of a character, which I think will be 1 byte. I could have written, if I wanted to read, integers, then it would be 4 bytes. And the 35 is how many to read. So if I would write the way I did it now, I'm going to read 35 characters, 35 bytes. But if it would be ints, I would write, it would be 35 times 4, 140 bytes. So that's why I need the size of, because the 35 is telling me whatever I'm reading, how many of them. But then I need to know how big they are, so I need a size of character. I could have just written, instead of size of character, I could have just written a 1 there. But you always want to use a function when you can, because then it's self-documenting. Then I see why there's a 1 there. And then FP is that pointer that I got, the file pointer. Notice I don't call it a file descriptor anymore. I call it a file pointer. Now we've got the file open for read. And what are we going to do? Well, the first thing we're going to do is, sorry, we opened it over here. We read something from the file. First thing I'm going to do is print what I read. If we go to the next page, we'll see that it read, this is the first line. I think that's 35 characters. I think I worked it out that that's 35 characters. So it prints the file. The first thing it does is it prints the buffer. Then it prints the word junk. Oh no, here's the contents of the file. Sorry, misunderstood. This is the contents of the file. This is the output. So the first 35 is, this is the file. This is the first line. This line, ha. That's the first 35 characters. And then the word junk. Well, that's because that's what I did here. I printed the word junk, then a new line. So I printed 35, then I printed the word junk. I just wanted to see if it really printed 35. Then I'm going to read another 35 characters into the same buffer. So I'm going to overwrite the buffer. And then I'm going to print that. So we see in the next slide that I print has, this line has, see the H-A-S, has 34 characters in it. This line has only, but only stopped, remember this line has only 17. It stopped up to the L. Why? Because I only read another 35 characters and I printed it. Now I want to jump ahead 23 characters. So this is a cool thing I can do. I have the fseek. There's an equivalent seek function, but I'm just showing you here. There's fseek. Sorry, just a second. I want to check something. Mhm. So, okay, sorry. Back to where we were. I rewound the file. Rewinding means I go back to the beginning. And then I print again 35. So after now I rewind the file, I should see the beginning of the file. Is that what I see? Now I write, this is the first line again. This is the first line, this line half. Now I jump ahead 23 characters. This from has here, if I jump ahead 23 characters, I get to this. This has only 17. So I write, this has only 17. But how much did I read? I read 35 characters, so I also read, so does this line. Now I jump ahead 23 by doing this seek. We can just go forward from the seek current, from the current location, 23 on this same file descriptor, file pointer. And then read 35 characters, then print junk. Now I rewind again.
Mhm.
And with rewind, I go again and I do read, big buffer, and read 350, print big buffer. So now I read again. This is the first line, and I print the whole thing. 350 and rewind again. Print the big buffer, reprint, rewind again, and then rewind. And then I read again. Oh, yeah, I rewind again. Here I read the big buffer. Wait, here I read the big buffer and I printed it. Here I read the big buffer again. Why am I doing that again? And I'm doing it properly. I'm putting in the 0 and then I'm printing it. Oh, I want to show you the difference. So I forgot to put in the 0 here. So, oh, but I cut off, I don't have the printout. The point is, I should have had another printout here. What happened, Mishi? You're hungry? What do you want to eat? No food? Did Baba make potatoes? You don't want? You want tuna? What do you want?